In this video, we will discuss tool operation, but before we can touch the actual hardware, we need to have a data file in the correct format to run on the tool. Crestech tools use a CON file format. For members with experience on avionics systems, those tools also use a CON file format, but other than sharing a name, these file formats are quite different from each other. We use the term CON file, but this is a catch-all term that actually refers to all the necessary files required to execute a write. A CON file itself is a human-readable text file that tells the tool what the field size and number of dots are, the location of any alignment marks, the relative location of each field, and the order in which fields are written. Think of this file as the set of instructions that tells the pattern generator what file to load next. CBC files are the instructions for the pattern generator. These files are machine readable, and the information in these files are what the tool actually executes when writing your pattern. There is one CBC file for each field. CCC files are, again, human readable. This is what the computer loads to display your graphics in the cable software. They are not required to execute your pattern, but they can be useful if you need to troubleshoot a pattern. As with CBC files, there is one CCC file for every field. All of these files are automatically generated in a folder, and when you transfer your pattern to either Crestech tool, you will want to transfer the entire folder over, not just a selection of files. Since the field size and number of dots is specified in the CON file, this means that every field called by that CON file must be that field size and number of dots. So, what if you want to write parts of your pattern at different resolutions? You will need multiple CON files to do that. In this case, it can be very helpful to set up a schedule file. In a schedule file, you can set up multiple CON files, which will execute in order from the top. You can specify relative stage shifts for these different files, which will come up in greater detail later, a dose shift or a dose multiplication factor if needed, or you can set up a matrix of the writing pattern. You can also use a schedule file to serve as a log file for the write that you perform on a given date. So, how do you make a CON file? 99% of the time, you will use the software Beamer to convert your design to the CON file format. As we've discussed, this process requires critical, design-specific choices like proximity effect correction and writing strategies that are too complex and pattern-dependent to cover in a general tutorial. We strongly recommend that you schedule a one-on-one with process staff to discuss your particular needs and help with your initial pattern conversion. We also want to refer you to the excellent webinars and tutorials shared by Genesis, the maker of the Beamer and Tracer software packages. Now let's look at the hardware itself. The NanoLab has two Crestech tools, the Crestech and the Crestech 130kV. The Crestech operates at 50 kilovolts. It has a min-max dose time of 0.1 microseconds and 650 microseconds, respectively. The dose time resolution is 0.01 microseconds. That means that you can specify a dose time of 0.1 microseconds, 0.11, 0.12, etc. The minimum beam current is 25 picoamps, and the maximum beam current is 7 nanoamps. It can fit samples up to 6 inches in diameter and up to 3 millimeters in thickness. For the Crestech 130kV tool, we operate at 100 kilovolts for stability. The min-max dose times are 0.1 microseconds and 65 microseconds. This allows us to have a finer dose time resolution, which is 0.001 microseconds on this tool. The minimum current on the 100 kV system is 50 picoamps. We can achieve beam currents much higher on this system. 100 nanoamps is theoretically possible, but we need a special setup above 20 nanoamps. The 100 kilovolt system can hold wafers up to 8 inches in diameter, and we can also accommodate 6-inch masks. Samples can be up to 9 millimeters thick. For both systems, the stitching specification depends on the field size being used. With better stitching for smaller rate fields. Overlay specification is 35 nanometers if using the 120 micron field and 50 nanometers if using the 600 micron rate field for both systems. Looking at the physical hardware, we can see that the tool is made up of multiple different subunits. On the very left, we have the main system with the exchange chamber or load block. Next, we have the electronics rack with the computer and control boxes in front of the user. And at the very right, we have the pattern generator. The setup for the Crestek 130 kV is nearly identical to the Crestek tool. The most obvious difference is that everything is just a little bit bigger. As with the little Crestek, the main system is on the left with the exchange chamber in the front. The electronics rack and the computer controls are next, with the pattern generator at the very right. There are two pieces of software required to operate the system. CRESSEM is the part of the software that operates the SEM components of the tool. The focusing, the stigmation, beam tune-up, all of those things are controlled by the CRESSEM software. Cable is the part of the software that controls the exposure. Think of the L in cable as referring to lithography. We will be using both pieces of software to operate the system. In the next part of the video, we are going to move through the basic operation of the tool. The icons shown here will help you stay oriented on which step we are on. We also use these same icons on the quick step guides that are available at each tool. This section is not designed to replace hands-on training at the system. You are still required to shadow a lab member at the tool before requesting qualification on the system. Loading a sample into either system is where we have the greatest risk of hardware damage. In the past, a lab member inserted a pallet into the chamber without the stage in place. In order to fix this, we had to do a full vent of the main chamber, which took the system down for an extended period of time. We have also had multiple instances of folks closing the load lock gate valve with the pallet not fully retracted. In the image on screen, you can see me pointing at the scar that was left in the pallet after one such misadventure. Take care when loading and unloading the sample pallets to be sure that the stage is in the correct position and the pallet is clear of the gate valve before opening or closing that valve. After loading your sample, the next step is to go and set the beam current that you need for your rate. To do this, we will go to the Faraday cup. This location is labeled FD for Faraday in the CRESSEM software. If you are on the Crestek 130 kV system, you may need to load an INI file to get your desired beam current. In CRESSEM, go to Setup Filing and then Read to load an appropriate INI file, which are parameter files with various hardware settings. On this system, there are different column configurations required to obtain all possible beam currents. You cannot get a 20 nanoamp beam current using the 50 picoamp column configuration. On the Crestek system, the 50 kV tool, we can reach all possible beam currents using a single column configuration. To measure your beam current, you will center the beam over one of the FD holes and then go into spot mode. The beam current is only updated when in spot mode. This value is also only accurate when centered over an FD hole. At any other time, it will undercount the current. You can now use the sliders and the control knobs to set your beam current. After setting the beam current, you can now navigate to your sample. Your first impulse will probably be to focus on your sample, but you don't want to start with that just yet. In an imaging SEM, you can navigate to a feature of interest, change the focus, and then collect your image. In an EBL system, if you unblank the beam so that you can check your focus, you will expose the sample in that region. You need to set the focus in an area away from your exposure zone. But samples are inherently messy. They have tilt, they have topography, and this can mean that when you move away from your focusing region to the region of interest, the sample could be out of focus. So, when you navigate to your sample, the first thing you want to do is to set a working sample height. You will do this either by setting wafer equals 0 or Z equals 0 in the CRESSEM software. You should see the sample height change when you do this. Now that you have a working sample height, when you execute your pattern, the stage will move up and down as needed to keep your sample at a consistent focal point. Now is when you want to zoom in and adjust the focus on the tool. After adjusting focus, you may want to move to the gold stub to adjust stigmation. On the left, we can see an SEM image of what the gold nanoparticles on the stub look like. On the right, we have the image palette from earlier. The arrow is pointing at the gold stub. You don't have to use the gold stub to adjust stigmation, but for larger beam currents and certain types of samples, it makes more sense to use this to adjust the beam than to attempt to do all adjustments on your sample. If you use the gold stub, you will want to start by adjusting the stage height. Remember, you just set this focus on your sample in the previous step. The gold stub is not at the same height as your sample, so you will need to manually adjust the stage height until the stub comes into focus. Then you can adjust stigmation. The next step is fine focus. For small beam currents and conductive samples, the easiest way to adjust the beam is by burning a contamination dot on your sample itself. To do this, you will turn spot mode on in CRESM for many seconds. The first dot might need 30 seconds or so in order for you to see it. Once you have a small dot, you can start making small adjustments to focus and stigmation in order to get a small circular beam. So at this point, you should have a nicely focused, well-stigmated beam at your desired beam current. But you're not ready to expose just yet. Remember all those fields that we spent much of video 2 discussing? We need to consider those now. We need to calibrate the tool for the given beam conditions to ensure that the fields are being drawn accurately. We don't want a stitching error at the edge of a right field. We want the scaling, rotation, and skew of each right field to be correct. And we want good alignment to underlying features. The calibration procedure that we run is called mark management. To run this, you will need to set lithography on in the CRESM software. This gives the cable software control over the stage and beam. In the Mark Management tab, you will not change any settings. Even if you are using a different field size, you always calibrate on a 600 micron field. All you need to do is click Execute. The tool will then make adjustments to 4 variables. ATTX is the X attenuation. This adjusts the scan field size in the X direction. ATTY is the Y attenuation. Same thing, just the Y direction. SRT adjusts the scan rotation, and RANG adjusts the orthogonality. RANG stands for right angle. What the tool will be doing is scanning the beam over a small hole, similar to the Faraday cup. It will scan both horizontally and vertically to identify the center of the hole. It will then move the stage and repeat this process until it has found proper values for each of the 4 variables. This process does rely on the tool being able to detect that hole. So when you execute mark management, the tool needs you to set brightness and contrast at appropriate levels so that the hole can be detected by the software. Other than that, the process will run automatically. We are finally at the point where we can run an exposure. But of course, we have even more choices. Our first choice is whether we want to run in raster mode or vector mode. Virtually everyone opts for vector mode, but raster mode has its use cases. In raster mode, the beam will raster to every dot in a field, and the beam blinker will determine if that dot is exposed or not. For sparse patterns, this is very inefficient, but for dense patterns, this can have significant time savings. The issue with raster mode is that it is not compatible with proximity effect correction. You can only expose at a single dose time for an entire con file. This is a significant limitation of this mode, which is why most folks opt for vector mode. In vector mode, the beam will only deflect to the defined shapes in the CBC files. Each shape can have a different dose time, depending on choices you made when creating the file. Both raster mode and vector mode each have 2 submodes that you can choose. Normal mode, a submode of raster, means that the areas inside a shape will be exposed. Inverse mode, the other submode of raster, exposes the areas outside that shape to the edge of the defined field. Vector mode does not have an inverse option. If you want to draw the outside of your shape, you will need to do that during the conversion process. The two submodes of vector are digital and analog mode. Digital mode is the default exposure mode. It has the best pattern placement and stitching. Analog mode uses an additional DAC to smooth the signal and is much slower than digital mode as a result. Please discuss use of analog mode with process staff if this is of interest to you. We are now going to do a rundown of all the different settings you can choose. Orientation and width will apply the corrections found during mark management. This should be on. Laser controls the stage position sensing laser. This should also always be on. Setting height sensor on will allow the stage to change the Z position to keep the sample in focus during the write. Sometimes some samples with a lot of topography may have an error with this setting. We recommend that this setting be on, but you can try writing with the height sensor off if needed. Height sensor offset will force a shift between the 0 of the height sensor and your sample. This is usually set to 0. Specimen thickness is the thickness of your sample. Putting the correct value here can prevent some height sensor errors. I will skip reg alignment for a moment. Don't worry, we will come back to this. Beam compensation is used in production environments. This should be set to off. Zigzag coefficient is used with the cable spot patterns. Unless you are using this patterns, set this to 0. Execution weight is used to delay a write after hitting exposure. This is usually set to 0. Coming back to alignment, we have 4 different alignment modes: off, rotational, absolute mode, and automatic mode. But before we can talk about alignment, we need to talk about pattern placement in general. We need to make sure we are writing our pattern on our sample, not at some random location on the stage. On the Crescec tools, the stage 00 is at the lower left-hand corner of the palette. All stage coordinates will be positive numbers. Both units of microns and millimeters are used. Pay attention to labels and convert where necessary. We will use a pretend graphene sample to walk through pattern placement. We want the electrodes to be correctly placed over one particular graphene flake. How do we go about doing that? The easiest way to think about this is to consider the origin of the design file. I want to map that origin to a known stage location. Where things get tricky is when you can't look at the origin. In this case, the origin occurs over one of the electrodes. So if we navigate to that location on our chip, we will have exposed that region. In this case, I need to know the dimensions of my chip. If I know that the pattern should be placed 2 millimeters up and 2 millimeters right of the lower left-hand corner of the stage, then I can correctly place the pattern where I want it on the chip. For this example, the lower left-hand corner of my chip is at stage coordinates 56.367 millimeters in X and 104.718 millimeters in Y. In option 1, we will physically move to the center of the chip before executing the write. We can either manually calculate the destination position and go there, or we can set up a relative move and use the arrow keys to make relative moves. Be sure to keep lithography on so that you don't accidentally expose your sample while moving. You can now read the stage position into cable. Click either the equal or plus equals buttons to specify this position for your con file. Once we've done this, we can see that our con file will execute at a stage location of 58.367, 106.714 millimeters. Alternatively, we can define a relative stage shift in cable, which it will execute when writing the pattern. In this case, we will stay at the lower left-hand corner of the chip, but in the cable scheduler, you will specify a stage shift of 2 millimeters in X and 2 millimeters in Y. For this example, both values are positive, but this will depend on which corner you are looking at and where you placed your origin. As in option 1, we read the stage position into cable, but now we must click the plus equals button. This adds our relative shift to the stage position. As with option 1, the con file will execute at a stage location of 58.367, 106.718. Both options yielded the same result, so use whichever method feels more comfortable or intuitive to you. A final comment. In EBL, there isn't a rule that you must place the origin at the center of your design. Place the origin in the location that makes the most sense to you. Here, we have 2 possible alternative origin locations, either of which would work. We can now return to the question of alignment. 0 layer alignment is what you will use if you have a bare sample with no lithography on it yet. You can either use off mode or rotational alignment. Off applies no corrections. Even if there are alignment marks in your con file, if you choose off, these marks will be ignored. Rotational alignment will allow you to apply a rotational correction, which helps correct for any sample rotation that might have happened when you loaded your chip into the tool. To use this mode, you will need to go to the Wafer Rotation tab under Mark Management. You will need to navigate to the part of your sample that you will be using for rotation correction, usually a sample edge. You will read in the first position, navigate to the second position, and then read in that stage location as well. This will allow you to ensure that your pattern is aligned to your sample, not to the stage when executing the rate. If there is already a pattern on your sample, you will want to align to that pattern. To do that, we use registration marks. Reg 2 marks are the global marks, and you need 2 of these marks. You will have an A mark and a B mark. The A mark should be below the B mark. Horizontal placement is arbitrary. If needed, you can include local registration marks as well. These are Reg 2-3 marks. You will need a single Reg 2-3 mark before any field where precision alignment is required. Both types of marks can be used with either ABS or auto modes. In ABS mode, you, the user, are doing the alignment manually. So the shape of the mark can be any feature you desire. You just need to know the design coordinates of the feature you are aligning to. For auto alignment, you must use Crestec to find marks. For Reg 2 marks, this is a cross that is 600 microns in length, with each arm being 3 microns in width. The Reg 2-3 marks are 40 microns in length, with the arms again being 3 microns in width. When executing an auto alignment, the tool will ask you to correct the positioning of the first mark and verify contrast and brightness before executing a search for the mark locations. The image in green shows what this can look like. We can see the original cross, and then there are faint scan lines across each individual arm, which is where the beam was scanning to find each arm to determine the position of the cross. It is important to remember that you are using electrons to see your marks. Just because something is optically distinct does not mean that it will be easily visible when imaging with electrons. An example of this is aluminum and silicon. These 2 materials are typically quite distinct from each other optically, but they are virtually identical when imaging with a high kV electron beam. So when considering what material you want to use for your registration marks, I recommend you follow Rook's rule of thumb. This rule comes from Mike Rooks of Yale University and has proven itself to be a very good rule of thumb over the years by the general EBL community. The rule states that the minimum thickness of your registration mark should be greater than 2600 divided by Z minus 14, where Z is the atomic number of the material in question, if Z is greater than 20. You can see that for different material choices, you may need a substantially different thickness in order to get enough signal to detect the registration mark. So how do you add registration marks to your con file? There isn't an option to add registration marks in Beamer. You will need to add them outside of the Beamer software. One option is to load your con file into the cable software via pattern data creation. There, you can add a Reg 2 marking or Reg 2-3 marking element. You can also just add registration marks directly into a con file. The syntax for an R2 mark is shown below. I do recommend that you check the number of digits. I have seen errors in the past when not enough digits are used for these marks. The syntax for an R23 mark is very similar. You just need to call this mark before calling the field for the local alignment. Executing alignment is easiest to explain during hands-on training. If you will need alignment, please ask your trainer or qualifier to demonstrate this to you at the tool. After exposing your sample, the final step is to unload your sample and leave the tool ready for the next user. And with that, this is the end of EBL class. Your next step is to take the EBL class test in Mercury. Thank you for your attention, and please reach out if you have any questions.